problems. Did those go okay? All right. Well, I want to start today with, so we're going to just do a few example problems on first law things. And I want to start with a list of things to keep in mind as we do these problems. So remember, what do I have? 5 things. The first one, this is the last thing we talked about last time. The work of expansion of a gas, well, it's also the work of expansion of a liquid, but it doesn't expand very much. It tends to be gases where we care about this. So the work of expansion is the integral from the initial volume to the final volume of the pressure times dV. Remember that this these volumes are the extensive property volumes. So, you know, often as we start working with tables and stuff, you're going to get stuff in terms of intensive volumes. You're going to have to convert that to use this. Okay. It is always the case that if the gas expands, W is positive. It does positive work on the environment. And if the volume decreases, then W is 0. Negative work is done on the surroundings by the gas, or you could say that the surroundings do work on the gas, do positive work on the gas. What do you need in order to compute that derivative?
P as a function of V.
Yep, that's right. You need P as a function of V, and if you're really lucky, P is constant. And then it's especially easy. So speaking of that, let's talk about, so we'll have a lot of cases where the problems we're doing are going to have V constant, P constant, T constant. Let's just talk for a second physically about how you would do that. Say you want to make a process happen where those things are, where volume or temperature or pressure are held constant. Okay, so first, this is the easiest one. To hold V constant in a process, how do you do that?
Closed system.
Yeah, I mean, I think like a fixed tank of some kind. A closed system, you could, like something in a piston, we'll still call that a closed system because we're not exchanging material with the surroundings.
Okay.
But yeah, a fixed walled tank and the volume is constant and that's the end of it.
Yeah.
Okay. How about to hold temperature constant? To do that, you most likely have to make your process happen pretty slowly, and you have to have your gas in thermal contact with a reservoir of some kind, you know. So you could have non-insulated walls and water rushing past copper walls or something, okay? And if the water is the same temperature, it'll keep the gas at that temperature. As long as your process isn't happening fast, too fast for the water to carry that heat away, you know.
What do you call that process again? Is that isothermal, or is that isothermal is when temperature can't change or can change?
Isothermal is holding temperature constant, yeah.
Okay.
So put the gas in thermal contact with reservoir at a fixed temperature. And then the last one you can hold constant is pressure. So how do you hold pressure constant?
Probably allow material to flow in or out.
Not necessarily. That is not necessary. So if we think of it as gas contained in a cylinder with a piston, all you have to do is apply a constant force to the piston, okay? And that constant force could just be the weight of the piston, or it could be a constant force that you're pushing down on the top of the piston. But as long as you do that,
because the force at the piston is the same the entire time.
The
pressure is the same in the system.
So yeah, like if you think of, here, let me finish writing this. To hold P constant, apply a constant force to the piston. Okay, so the piston is being held in equilibrium. And again, this requires a slow enough process for this to work, but it's held in equilibrium by a force pushing down and the gas pressure pushing up, okay? And so if this, and those always have to be in equilibrium, you know, at any instant. And so if you keep pushing down with the same force here, the gas volume is going to change to a point that those are in equilibrium, and that means the pressure stays the same.
Yeah, because by definition, for it to be in equilibrium, that force has to be constant and equal opposite.
Exactly.
Okay.
Yep. And then the last thing, I'm going to lump these two together. So we'll see cases where, so if you're given pressure is equal to A times V to the power of B, where A and B are just some constants. Those can be different in different cases. Or when you'll see it written like this, sometimes P times volume to the power of N is a constant. Okay, that's just saying that for the process that you're dealing with, those are experimental things that have been found to be more or less true, okay? There's no, that's not like a law of physics or something. It's just sometimes you'll see that that fits the behavior pretty well. So these are just experimental findings for a specific process. Okay, so now we're just going to do a few example problems with the first law. So the first one. So let's say the gas pressure is constant. At a pressure of 1.3 times 10 to the 5th pascals. It starts at a volume of 0.35 cubic meters. Then the temperature is reduced. And the volume decreases to 0.20 cubic meters. What's W for the gas? Yep. Yep. All right, well, we're going to use the integral for the work of expansion for this. So work is the integral of P dV. We have P constant. That makes it easy. Our starting volume is 0.35. Our ending volume is 0.20. Our pressure is 1.30 times 10 to the fifth. And so this just becomes 1.30 times 10 to the fifth times 0.2 minus 0.35. And if you multiply that out, you get 19,500 joules negative. Okay, so W is negative. Does that mean that the gas is doing work on the surroundings, or the surroundings are doing work on the gas?
The surroundings do work on the gas.
That's right. And you can also see that, if the volume is decreasing, it means the surroundings are pushing in, doing work on the gas. You know, that's another way to think about it.
And since it's minus W, the change in energy would then be positive. Makes sense.
That's right. That's right. The change in energy would be positive. The gas energy would go up. Okay, here's another one. So I guess both of these first two, they don't have to do with the first law. They're just calculating this integral. So for this one, let's assume for this process, P times V to the power of 1.2 is a constant. During this process. At the start, we have a pressure of 3 bar. 1 bar is 1 times 10 to the 5th pascals, so that's 3 times 10 to the 5th pascals. And the volume at the start is 0.1 cubic meter. And then we go through the process and we end up with a volume at that second instant of 0.2 cubic meters. And we want to calculate the work. Okay, so the way this works, this is one of those two examples I gave in number 5 of those things to remember. It's a relationship between pressure and volume. Notice that the one that we're looking at right now is this, right? there's one variable, one value that we don't know, one constant that we don't know. We're given that n is 1.2. We just don't know what that constant is. Okay. So in order to find that constant, we need a relationship between pressure and volume at one instant, and that's all. Right? That makes sense. We're just calculating one variable. In this case, if you see something like this and you have two constants that you have to solve, then knowing the pressure volume relationship at one instant isn't going to be enough. You have two variables, you need two equations to solve for them. Okay? So in a case like this, where A and B are both unknown, you need to know the pressure and volume at instant 1 and the pressure and volume at instant 2. Okay? In our case, we only need pressure and volume at one of those two, and we have it at instant 1. Okay? All right, so the first thing we have to do is find that constant. So we have P V to the power of 1.2 is equal to C. We want to find that C. So plug in the values where we know P and V. So 3.0 times 10 to the 5th is P times 0.1 to the power of 1.2. And that's equal to C, and that just lets us calculate C directly. So C is equal to 18,928.7. And it has some units, but our units are in SI, so we know everything's going to work out, so I'm just going to treat that like a number. And now the only thing we have left to do is we want to take that relationship P to the power of 1.2 is equal to C. Well, we know what C is now, right? But we want to express that as P as a function of V so that we can use the integral. Okay, so what we have now is P times V to the power of 1.2 is equal to 18,928.7. Now multiply both sides by V to the power of negative 1.2. So P is equal to 18,928.7 times V to the negative 1.2. You're going to have to get, for these kind of problems, you're going to have to sort of refresh your memory if you haven't done it in a while on manipulating these exponents, because we're going to have variables we have to solve for that are in the exponents and stuff. You're going to have to remember the exponent rules and stuff. But now we have pressure as a function of volume. That means we can compute this integral. So work is equal to the integral from volume 1 to volume 2. So that's 0.1 to 0.2 of 18,928.7 V to the negative 1.2 dV. So now you have to use, the exponent rule for integrals. So W is equal to 18,928.7 V to the negative 0.2 divided by negative 0.2. And we're evaluating that from 0.1 to 0.2. That's our volume. And you get a value of 19,417.4. Everything's in SI units, so this has to be in joules. Any questions about that? Does it make sense that our value for work is positive? And what information do we have to check that? The volume increases, exactly. The volume increases, so W has to be positive. Yep. Okay, so those are a couple of problems where you're computing the work of expansion. That can also be a step in a first law of thermodynamics problem. So now let's get into some problems with the first law of thermodynamics. So remember the first law of thermodynamics says the change in energy of your system is equal to Q minus W. Q is the heat that's added to your system. W is the work done by your system. And you can expand that so if we expand, delta U is equal to the change in kinetic energy plus the change in potential energy plus the change in internal energy. That internal energy is going to be more important to us in this class, but I think this first example is sort of a contrived example where we have all those things going on, so you can see how it all works. And that's equal to Q minus W, and that W, well, there are a few ways that you can have work done, but one of those is the integral of PdV, and that's one that we're going to see pretty often. You can also have electrical work done, and so we could expand this one more time. The change in kinetic energy is 1/2 times the mass of your system times the change in the speed squared. The change in potential energy, if we're talking about gravitational potential energy, this is mg times the change in height of your system. Plus the change in internal energy is equal to Q minus W. And actually, don't write the W like that. Let's write it as minus W that's not due to expansion minus the integral of PdV. That's about expanded about as much as we can for now. Okay, so here's the first example problem. Let's say that our system is a 0.5 kilogram combination of the gas and the container that it's held in. So usually our system doesn't include the container. This time it does. Let's say 100 joules of work and 50 joules of heat are added to the system. As this happens, the system goes from rest to 3 meters per second. And lowers a distance of 2 meters. What's the change in the system's internal energy?
The internal energy is delta U?
Delta U, yep. And so, really this is just a matter of plugging values into this fully expanded form that I just gave here. For the change in energy, the left side of this equation, that is the change in kinetic energy plus the change in potential energy plus the change in internal energy. The change in kinetic energy is 1/2 times the mass of the system. What did I say that was? Half?
0.5 kilograms.
Okay. So the mass of 0.5. And it started out at rest and ended at 3 meters per second. So this is times 3 squared minus 0 squared. Okay, this is the change in kinetic energy of the system. Then the gravitational potential energy of the system is the mass of 0.5 times G 9.81. That's positive, remember. If you ever forget about the sign of G, remember you can always think about it in terms of potential energy. Does the gravitational potential energy of something get bigger as it gets higher or bigger as it gets lower? Bigger as it gets higher, and in order for that to happen, that G has to be positive. The change in height is -2 meters. That's given in the problem. It lowers 2 meters. And then plus delta U. We can calculate this 9/4, so 2.25 minus 9.81 plus delta U and now we'll go to the second side of this equation. Well, let's see, what is that? -7.56.
That's what I got.
Okay. -7.56 plus delta U. So now we'll go to the first law. That says that the change in energy, -7.56 plus delta U, is equal to Q minus W. So what does it say about Q and W? It says 50 joules of heat is added to the system. So if heat is added to the system, is that positive or negative Q?
Positive Q.
Positive Q, yep. So negative 7.56 plus delta U is equal to positive 50. And it says 100 joules of work is added to the system. If work is done to the system, is that positive or negative W? Negative W. So we have minus W. In this case, W is negative 100. Anybody want me to flesh that out a little more? Or are you getting used to this sign convention? Hopefully, little by little, it'll become sort of natural. And so we have 150 minus 7.56, so delta, 150 plus 7.56, so delta U is equal to 157.56, and the units are joules, because we're in SI units. Any questions about that? Okay, let's do another one. So let's say during this process, pressure is known to follow this form A times volume to the power of B. And let's say that 200 joules of heat is added. And let's say that we start out at a pressure of, so P1 is 2 bar, or in other words, 2 times 10 to the 5th pascals. And volume 1 is 0.3 cubic meters. And then at the end of the process, P2 is 0.5 bar. And V2 is 1.5 cubic meters. We'll assume that there's no change in kinetic or potential energy. That's a little confusing because we have 2 capital V's going around. I'll just write that as potential energy. I'll write this as kinetic energy. What's the change in internal energy? Okay, so notice that we did one before where we had PV to the power 1.2 is equal to a constant. We had one unknown. In this case, we have the one where we have the two unknowns, A and B. That means in order to do that, we need to know pressure and volume at both of the two instants. So we have it, right? In the last one, we only needed it at the first instant. And so we should have everything we need. Why don't you take, I'm going to pause for a minute. Why don't you take a few minutes, see if you can work through this. Feel free to talk to each other about it or ask me questions. And then when you're done with that, I'll go through it and just, we'll try to solidify this stuff in your brains a little. So we're ignoring kinetic and potential energy. That means that in this case, the equation we're dealing with is that the change in U is equal to Q minus W. And W is just work of expansion, so it's just going to be that integral. So let's figure out what work is. So work is PdV from volume 1 to volume 2. In order to do that, we need to know pressure as a function of volume. So P1, we know P is equal to A times volume to the power of B. So at state 1, we know that 2 times 10 to the 5th is equal to A times 0.3 to the power of B. And we can use that to express A in terms of B or B in terms of A and substitute it into what we know from the other one. I guess I'll write this as A is equal to 2 times 10 to the 5th divided by 0.3b. I'll just leave it like that for now. And then we'll go to the other one at instant 2 that says 0.5 times 10 to the 5th is equal to A times the volume at instant 2, 1.5 to the B. And now we can substitute A in for this. And we get 0.5 times 10 to the 5th is equal to 2 times 10 to the 5th times 1.5 to the B over 0.3 to the B. And divide both sides by 2 times 10 to the 5th. You have 0.25 times 10 to the 5th is equal to, we can write this as 1.5 over 0.3 all to the power of B.
You got an extra factor that comes a bit on the left-hand side.
No, you're right, I do. Thank you. Thank you. And so this is, 1.5 divided by 0.3 is 5, so we have 5 to the B. Now we can take the natural log of both sides, and we get natural log of 0.25 is equal to B times the natural log of 5. So B is equal to natural log of 0.25 divided by natural log of 5. And you get B is equal to negative 0.861. now you can plug that back in and solve for A. So A is equal to 2 times 10 to the 5th divided by 0.3 to the negative 0.861. And you get A is equal to 70,930. All right, so now we can finally express P as a function of volume. P is equal to 70,930 times V to the negative 0.861. And so the work is the integral from the starting volume to the finishing volume. So from 0.3 to 1.5 of 70,930 times V to the negative 0.861 dV. The polynomial rule for integrals says that this is equal to 70,930 to the power of, so one more than this is 0.139. So 0.139 and divide by 0.139. And evaluate this from 0.3 to 1.5. And the number that I have written down here is 226,447.
Yeah, I'm still getting about 108 instead of
Anyone else?
26,000.
I don't have a calculator with me. Did you get an answer for that, Laura?
I actually ran, well, okay, I created the numbers here
Mm-hmm.
from the B.
Yeah.
And so the number that I got for A was 79.
Oh, really?
Yeah, I got 7,900 too.
7,900, not 70,000.
Well, I should say 70,000.
Oh, okay. Oh, okay. So I'm just, our rounding is different. Okay. That won't make a difference of, yeah, that won't make, yeah. Let's see. Well, I wrote this wrong. This should have be V to this power. 70,930. Okay, well, I guess let's do it. So 1.5 to the power of 0.139. Can at least two people do this, and we'll find out who's wrong here.
Is it for 1.5?
Yeah, do it for 1.5.
I have 1.0579 about, or well, I guess.
Okay.
97.
Oh, and can you do 70,930 divided by 0.139?
Yep. Yeah, so 70,930 divided by 0.139.
Yeah.
Is, 510,288 about.
Okay, so we got that. Times, and what did you say 1.5 to the power of 0.139 is?
Yeah, I'm getting 1.058 about.
0.58, okay. And then what's 0.3 to the power of 0.139?
Getting 0.846.
846. Those make sense with what you're getting, Laura? Okay, and then multiply that out.
getting 108, 181.
Okay. God dang it. Okay. Positive 108, 181 joules. Does it make sense that it's positive? Yes, the volume increased, so it's positive. Now we have the work that's by far the most time-consuming part of this problem. So now,
Yeah, because we just needed the work in the heat.
Yep, and so the change in internal energy is equal to, it says 200 joules of heat is added to the system, so we have 200 minus 108, 181, and so we get about negative 10, what's that, 7, 10, yeah, can you subtract that for me? $107,981,
Yeah, 107.981. Yeah.
981 joules. So there's a decrease in internal energy of the gas.
A quick
Yeah.
question with log rules. I use natural log also, but isn't it true you can use a log of any base and that same rule where you pull down the exponent applies? Is that how it works?
Let's see.
Like if I use log base 10 instead of the natural log for the algebra?
I don't remember. Okay, let's do a problem like this with where we're including intensive properties, and you have to go back and forth between intensive and extensive properties. Okay, so let's say that again we have a piston and a cylinder. And this is the gas. And let's say that the piston has a mass of 5 kilograms. And it's free to slide up and down in that cylinder. And let's say that we have 1 kilogram of gas. And it goes from a specific volume of 0.5 cubic meters per kilogram to a specific volume of 0.3 cubic meters per kilogram. And let's say that the area of the top or the bottom of that piston is 0.02 meters squared. We want to calculate the pressure of the gas. And then if the cylinder is insulated, what's the change in internal energy of the gas? Okay, so first we have to find the pressure of the gas. And this is a case where notice that the force applied to the gas by the piston is constant because it's the weight and the weight is constant. And so the pressure in that gas is going to be constant through the whole process. So if I draw a free body diagram of the piston, we have a weight acting down of 5 kilograms times 9.81, so 49.05. And counteracting that is the force pushing up from the gas pressure. That's the pressure times that area of the piston. So this is going to be 0.02 P. And if we're assuming that this is an equilibrium at every instant, again, this has to happen slowly for that to always be true. It's what's called a quasi-equilibrium process. You can assume that at every instant this is an equilibrium. Then Newton's second law says 49.05 is equal to 0.02 P. And so P is equal to 1.0345 times 10 to the 5th pascals. A lot of significant figures all of a sudden.
Getting 2,452.5. Anyone else is getting that?
Where am I getting these numbers? Oh, I know why. Yes. Okay, because I forgot something important here. I forgot the atmospheric pressure.
Oh, for your free body guy.
Yeah. So there's an additional force here that's on the pressure from the outside, and that is 0.02 times the atmospheric pressure, which is 1.01 times 10 to the 5th. So we have 49.05 plus 0.02 times 1.01. It looks like that comes out to be about 2020.
Yep, that's what I got.
And that's equal to 0.02 times the pressure. And now if you solve for P, hopefully you get 1.0345 times 10 to the 5th pascals. (2020).
Yep, that looks right
Okay.
to me.
So, yeah, remember how significant atmospheric pressure is. It's applying gigantic forces to everything all the time. That thing is 5 kilograms. That's pretty big, that's a 10-pound piston, but the force of the weight of that is just dwarfed by the pressure of atmosphere pushing down on it.
Yeah, by a factor of 40.
Yeah. Okay, so now that we have that pressure, and that is the pressure at every instant through this process. So now we can calculate the work. So the work is the integral from the first volume to the second volume. Before we do that, we need to calculate what those volumes are. because you need to use the extensive volume in that integral. So volume 1 is equal to the mass, 0.1 kilogram. Oh, here I said 1 kilogram. Here I said 0.1. Let's stay with what I wrote in the problem statement. So 1 kilogram of gas times 0.5, that's the specific volume, gives you a volume of 0.5 cubic meters. And then the second volume is 1 times the volume of 0.3 cubic meters per kilogram. And so that gives us a volume of 0.3 cubic meters. So now we can calculate the work. It's the integral from 0.5 to 0.3 of 1.0345 times 10 to the 5th dV. So that's 1.0345 times 10 to the 5th times negative 0.2. And what do you get for that?
Negative 2,069.
Negative. Should it be negative 20,690? Okay. 20,690.
Oh, yeah. I put 029.
Yeah.
That makes sense.
Okay, joules. Does it make sense that the work is negative? The gas is contracting, the volume's getting smaller, so it should be negative. And now we can finally use the first law, and that says that the change in internal energy is equal to Q minus W. It's insulated, so there's no heat transfer, and so that's 0 minus negative 20,690, and so you get a change in internal energy of positive 20,690 joules. Because I said that the cylinder is well insulated or insulated. And so insulated means that there can't be any heat transfer with the surroundings. Any other questions about that one? Okay, let's stop there, and next time I'll talk about methods of heat transfer, how to calculate heat transferred by conduction, convection, and radiation. Okay, that's all.
I have one last question.
Yeah.
You're done.
Yeah.
What's the purpose for using specific volume?
Yeah, so we haven't seen it yet, but when we start using element tables that are going to relate pressure and volume and temperature and entropy, it's all going to use specific values, because otherwise you'd have to have tables for your specific amount of...
Oh, okay, yeah, because we're using different gases and they're not all necessarily going to be the same.
Well, it'll be for different gases, but you don't want to have a table that has entries for half a kilogram and a separate entry for a third of a kilogram and a separate, you know.
Yeah,
And so the specific lets you have one table that works no matter
Yep, and you're just.
what amount of material, that's right.
Okay.
Yep. Yeah. Okay.